This is the first part of a three-part series on periodic trends. But first, some background. As electronic structure changes, the properties of the atom change. These include the size of the atoms and the ions, the ionization energies, or how easy it is to remove an electron affinities. This is the change in energy when an electron is added to an atom to form a negative ion, or the likelihood of an atom gaining an electron, and electronegativity, the tendency for atoms in a covalent bond to hold onto or hog electrons. These properties affect the behavior of these elements in chemical reactions, which is why we care about them. Periodic trends happen because of the different forces that are working on the electrons. These forces are governed by Coulomb's law, which you should be familiar with. The Coulombic force is proportional to the product of the charges involved, divided by the square of the distance between the nuclei of the two charges. And note that this is an inverse square law. If you're familiar with gravity, this is very similar. The force can either be positive, attractive, or negative, repulsive. The larger the charges are, the stronger the force is. The farther apart the charges are, the weaker the Coulombic force is. And the closer together the charges are, the stronger the force is. And these are very important to keep in mind when we talk about periodic trends. Now let's talk about the forces on electrons. Most, if not all, periodic trends can be explained by the number of protons in the atom, the arrangements of the electrons in the atom, and the forces electrons exert on each other. Forces add up in an atom, and an electron may feel a combination of forces. One very important thing to remember is as more protons are added to the nucleus, the attractive force between the protons and a given electron increases. As more electrons are added to an atom, however, there is an increase in the repulsive forces between the electrons, and this can result in a phenomenon known as shielding. Let's talk about shielding. Core electrons can block or decrease the amount of positive charge from the nucleus that a valence electron feels. Because of this, it makes a valence electron a little less attracted to the nucleus. We call this shielding. Now take a look at this picture. The core electrons are in inner shells, below where the valence electrons are. And the repulsion from the core electrons can prevent the valence electrons from feeling the full positive charge of the nucleus. Now, valence electrons can shield each other a tiny little bit because electrons are going to repel each other no matter where they are. However, the core electrons are the ones we are most concerned about. They are our key players. So when you think about shielding, focus on those core electrons. Now, all of this attraction and shielding adds up to something we call effective nuclear charge. There is a balance between the attractive forces between the electrons and the nucleus and the repelling forces or shielding caused by the other electrons in the atom. And this balance is responsible for a lot of the periodic trends we see. We can quantify the total forces on an electron by considering effective nuclear charge, often represented by Z subscript EFF, Z effective. The effective nuclear charge is the amount of positive charge from the nucleus that the electron actually feels. Now, here is a simplified equation where Z effective is the effective nuclear charge, Z is the number of protons, and S is the average amount of electron density between the nucleus and the electron, in other words, the shielding. When you think of periodic trends and what's causing them, think about that balance between the attraction of the nucleus and the shielding from those core electrons. Note that even though electrons in the same energy level do repel each other a tiny bit, it's the core electrons we're more concerned about when it comes to periodic trends because they have a much larger effect. The higher the effective nuclear charge, the more attractive force the electron feels from the nucleus. Effective nuclear charge varies by location on the periodic table. As you move to the right across a row, each element has one more proton than the element to the left of it. The nuclear charge gets larger. Hence, as you move to the right, the electrons in the element feel more and more pull from the nucleus as the amount of positive charge grows. However, because all of the elements in a given row have valence electrons that are in the same energy level, they all experience about the same amount of shielding. In other words, they all see the same core electrons. They're shielded about equally. And as a result, the effective nuclear charge increases as you move from left to right. You add protons, but you have about the same shielding. As you move down a column, the effective nuclear charge also increases because you are adding more protons. The core electrons are especially affected by this, and they tend to be pulled in tighter towards the nucleus. But as for the valence electrons, there are other things that have a larger effect on periodic trends, and we'll talk about that in a minute. Spoiler alert, the increasing distance of the valence electrons from the nucleus as you go down a column and add more shells is a huge deal. And we will be coming back to this over and over again. The periodic trend this video is going to focus on is atomic radius. Now, the size of an atom is determined by its atomic radius. And we define an atomic radius as 1/2 the distance between the nuclei in a molecule consisting of two identical atoms joined by a covalent bond. We define it in this way because it's really difficult to tell where the edge of an atom is. Remember, we're dealing with all these quantum probability clouds. The atomic radius gets smaller as you move across a row from left to right. And remember that as you move across the row in the periodic table, you add more protons. And as you add more protons, the effective nuclear charge gets larger. The electron feels the positive charge more strongly. But the shielding doesn't change much because all the valence electrons in the same row are in the same shell, and they have the same core electrons. So with the higher effective nuclear charge, electrons get pulled closer to the nucleus, and the radius gets shorter, and the atoms get smaller as you move from left to right across the row. Within a row, valence electrons are all feeling about the same amount of shielding, but the positive charge on the nucleus gets larger. And according to Coulomb's law, the larger the charge, the stronger the force, and this force is enough to pull those electrons in tighter. And looking at Coulomb's law, we can see as the nuclear charge increases, the force on the electron also increases. Now let's go down the column. As you go down a column, the positive charge in the nucleus increases, and the core electrons are being pulled in tighter. We can see this in photoelectron spectroscopy, which is also covered in this unit. However, as we go down the column, the valence electrons are added to higher and higher energy levels, and they get farther and farther away from the nucleus. Per Coulomb's law, as we increase the distance between the charges, that force is going to decrease. And the atomic radii get larger because we're adding shells. Now, this is a graph that shows the trends in radius size versus atomic number. Take a look at this more closely and see if you can notice any particular trends. Now, this is something you're going to look at more closely in class. Now let's talk about ionic radii. Think of it as the atomic radius of an ion. Ions are formed when neutral atoms either gain or lose electrons. And an ionic radius is influenced by the same factors that determine atomic radii: the charge of the nucleus, the distance the valence electrons are from the nucleus, the amount of electron repulsion, including shielding. Ions can be larger or smaller than their parent atoms depending on the charge. Let's look at cations first. A cation is formed when electrons are lost. Cations are typically formed from metals on the left side of the periodic table. When cations are formed, the parent atoms often lose as many electrons as they need to have a full outer shell that looks like the electron configuration of the nearest noble gas. This makes them more stable. When cations are formed, an entire principal energy level may be lost. Also, when a cation forms, there are now more protons than there are electrons. There is a little less shielding, and the electrons get pulled in tighter. The result is the cation is smaller than its parent atom. Cations are smaller than the parent atoms from which they were derived. Now let's talk about the ionic radius of an anion. An anion is formed when a parent atom gains electrons. Anions are typically formed from nonmetals on the right side of the periodic table. When anions form, the atoms typically gain enough electrons to have a full valence shell that looks like the electron configuration of the nearest noble gas, typically the noble gas on the right. Anions have the same number of protons as their parent atom, but more electrons. When new electrons are added to the shell, there is a small increase in the amount of electron shielding. The extra electrons interact with each other and they repel each other even when they're in the same energy level. Z effective is smaller than it was in the neutral atom because of the little bit extra shielding, and the electrons are not pulled as close to the nucleus. An anion is larger than the parent atom from which it was derived. Atoms and ions that have the same electron configuration are said to be isoelectronic. Here are some examples of isoelectronic species, and they also include the electron configuration. In this top row, all of these ions have the 1s2, 2s2, 2p6 electron configuration. And below that, all of these have the 3s2, 3p6 valence electron. We wrote this one, of course, in noble gas notation. Now, for atoms and ions that are isoelectronic, the number of protons is what's going to determine the size. The greater the nuclear charge, the smaller the radius is going to be if you have a series of isoelectronic atoms and ions. And if you look at this chart, this is very easy to see. If you're looking at your notes, you might want to take your pencil and color your black and white diagram in to look like this one. The ionic radius for anions is depicted in blue. The ionic radius for cations is depicted in red. And let's take a look at the top row starting with oxygen. And we're going to look at the ionic radii. We go from 126 to 119 to 116 to 86 to 68 as we increase our atomic number, and likewise increase the number of protons in our nucleus. We see the same trend as we move from sulfur all the way through gallium, where the size of the ionic radius decreases. So let's summarize. Today we talked about the forces that act on electrons and the relationship of these forces to Coulomb's law. We talked about effective nuclear charge. We talked about trends in atomic radii. Radii get smaller as you move from left to right across the row because of increased effective nuclear charge and the increased number of protons in the atoms. Radii get larger as you go from top to bottom because of increasing distance of the valence electrons from the nucleus as you add more principal energy levels or electron shells. We also talked about ionic radii, how the radius of a cation is always smaller than the radius of its parent atom, and the radius of an anion is always larger than the radius of its parent atom. And this all has to do with the interplay of attractive and repulsive forces and Coulomb's law.